All right, so we're live on YouTube and we're recording. So welcome everybody, good morning, good afternoon. Today we're gonna have the seminar by Carroll. And just a reminder of the format, Sean is gonna give a shortish presentation between 30 and 50 minutes. And then we're gonna have ample time for question answers, Q&A session and discussion session as well. So if you have a question that is like a clarifying question, please unmute yourself and just ask it. But for more like substantial discussions or objections or stuff like that, let's keep it for later. And I don't think Sean needs too much of an introduction. So Sean, I just leave you to talk about it.
Thank you very much. I appreciate very much. So just so you all know two things. Number one, I am in Mountain Time, United States right now, so it's very early in the morning for me, even though it's not for you. So be gentle on me that way. And Andrea did ask me to give a 30-minute talk, but then I double-checked and he said, well, really, it's between 30 and 50, so it will be 50, naturally. That's the mistake that he made. And the idea today is we're going to talk about part of a program that my collaborators and I have been thinking about for quite a while now in stripping down the, if you want to be a philosopher, the ontology of quantum mechanics to the very bare minimum. To think about the fundamental reality that we live in as being described by a vector in Hilbert space evolving according to the Schrödinger equation. And in many versions of quantum mechanics, that's true, but the emphasis here is that that's all you have to work with, nothing else. And can you possibly go from those bare bones ingredients to the enormous complexity and richness of the world we see around us? The answer is, we can successfully do the first step of the 1,000 steps we have to do. So the augurs look good so far. So to start here, let's see, there we go. Just to remind you, and it's going to get more complicated than this, but I'm reminding you how you were taught to invent quantum theories. And of course, there's a whole bunch of ways in which we can, quote unquote, quantize a classical theory. Here's one of them. You start with a classical theory. This is what physicists do when they start quantizing theories. They start classical because, that's how we grew up, okay? It's not how nature works. Nature is never classical. It's quantum from the get-go. But we are given, for example, a Hamiltonian, what I call a classical precursor theory. And here's the simplest one: single particle moving in a single dimension with a potential energy. And then what you do is you construct a quantum theory from that by inventing what we call wave functions. So you take half of the classical phase space, either position or momentum or some cleverly chosen combination thereof, and you invoke square integrable complex functions of that half. So let's say the coordinate for definiteness, right? So you have a wave function, a complex valued square integrable function of what used to be the position. And then you say that it obeys Schrödinger's equation. So you can promote the wave function to something that has a set of operators acting on it. What used to be an independent variable, the momentum, is now a differential operator on the wave function. And the Hamilton's equations of the classical theory turn into Schrödinger's equation of the quantum theory. And we're all familiar with this. Hopefully this is all very elementary. And so then you notice, or if you're von Neumann, you notice that this set of things you've invented called wave functions form a vector space. And he invented the term Hilbert space for the kinds of vector space you have here. It is a complete, complex, normed vector space. So rather than expressing the quantum state as a function, a complex valued function of the position variable of classical mechanics, you can just express the quantum state as a vector in a Hilbert space in a very abstract sense. And then that position function turns into a representation of that vector space. But in this way of thinking, it's the vector space that really matters. The position comes later in some sense. You have an abstract vector, you can add them together, scale by complex numbers, take the inner product. That's what we've all learned. So if at the end of the day, someone says, what do you mean when you say I have a quantum mechanical theory? You're not allowed to, I'm not allowing you to say, well, I started with this classical theory and I quantized it. What do you intrinsically mean when you have a quantum theory? Basically, all you have, all the specification you need to pick out which quantum theory you have, is the dimensionality of Hilbert space and the Hamiltonian. The Hamiltonian is what gives you the dynamics of that vector on Hilbert space. Now, there's a technical complication that I would go into if this were an hour-long talk, but I won't go into it because it's a 50-minute talk, which is if we had an infinite dimensional Hilbert space, then there's more work to do because you have to pick out what observables you have in your infinite dimensional Hilbert space. But I claim that you don't effectively have an infinite dimensional Hilbert space because of gravity. The Hilbert spaces I'm going to care about are trying to be realistic, and I claim that those are finite dimensional, at least when describing some finite-sized region of space. So in quantum field theory, or even in just any single particle moving in a potential in non-relativistic quantum mechanics, it's well known that the Hilbert spaces we deal with are infinite dimensional. We started with a continuum, we quantized it, we get an infinite dimensional Hilbert space, okay? So gravity acts as an extra kind of cutoff. If you started with a quantum field theory and put an infrared cutoff, so you say I'm only working in a box, and put an ultraviolet cutoff, so you have the Planck scale or some small scale discretization of space-time, for example, you would still have an infinite dimensional Hilbert space because every mode in the box is still a simple harmonic oscillator-like and has an infinite spectrum. But gravity doesn't let all of those states be real because those states become arbitrarily high energy. And if you try to excite an arbitrary amount of energy in a finite-sized box, eventually you hit the point where you make a black hole. And any extra energy you try to put there makes the black hole bigger than the box, and so it's not allowed. So gravity gives you an extra kind of cutoff on the allowed physical states in your theory. And this is not very perfectly well understood. I'm going to certainly say that, admit that. But I think that the lesson here is that when you think about describing what we think of as a finite-sized region of space in a realistic quantum theory, there's only a finite number of states available in that region, so therefore a finite-dimensional Hilbert space. And we even know what it is. The dimensionality of the Hilbert space goes as e to the area in Planck units, which can be very, very big. For a cubic centimeter, it's like, I think 10 to the 10 to the 66 or something like that. It's a big number, but it's still finite. And what that means is you don't need to tell me the observables of your quantum theory. The observables are every Hermitian operator in this finite dimensional Hilbert space. There's a profound corollary of this way of thinking, which is that quantum field theories have infinite dimensional Hilbert spaces, quantum gravity doesn't. Therefore, quantum gravity is not a quantum field theory. I think this fact, I think it's a fact, at least it's a very plausible conjecture, is super profound and doesn't get a lot of attention when people talk about quantum gravity. You know, people, we all want to like just construct our favorite theory of quantum gravity and then give it to you. But even without constructing the specific right theory, I think this is one of the very few but very powerful pieces of guidance we have about constructing quantum gravity. It's not a field theory, at least not in the conventional sense. Maybe you start with a field theory and then cut it down in some way. That's fine. Okay. So what does this leave us with in terms of thinking about how to think about the fundamental laws governing the nature of reality, right? We want to explain how the quantum theory of everything, once we eventually have it, gives rise to the rich, populated classical world that we see with space-time and fields and tables and chairs like that. But the fundamental beginning point is just a vector. And that vector is evolving via a linear equation. It's a very simple equation, right? The Schrodinger equation is kind of, not that complex, especially in a finite dimensional case. So when we speak the language of classical physics, fields, particles, forces, somehow none of those are there when we start. We started with a vector in Hilbert space, and that's it. We can subdivide Hilbert space and talk about entanglement and density matrices and things like that. But somehow all this classical language has to emerge somehow. And that is not, it's not a trivial task, right? We usually put it in by hand and cheat. I'm trying not to cheat is what we're doing here. So just to really drive it home, I'm going to say the same thing I just said, but slightly in different words. You might think that when you are given a Hamiltonian, the Hamiltonian not only sort of gives you an operator on Hilbert space, but in some sense conveys what the theory is about, right? Here is a Hamiltonian for a simple harmonic oscillator, the quantum Hamiltonian, right? And you can look at this Hamiltonian, and once you've taken your quantum mechanics class, you go, I know what that is. It's a harmonic oscillator, okay? So I know the meaning of it, not just the mathematical form of it. But I claim that you've been cheating a little bit because you've been giving me the Hamiltonian in a very specific basis. This is the position basis of non-relativistic quantum mechanics. So how did we know ahead of time that that was the best basis, the right basis in some sense? I mean, we know that there are other bases for the harmonic oscillator, right? You can use the energy eigenstates or something like that. So if all I have is the Hamiltonian as an abstract Hermitian operator on a finite dimensional vector space, there's no preferred basis in which I should be expressing that Hamiltonian, except perhaps for the energy eigenbasis, right? The Hamiltonian itself defines a basis, the energy eigenbasis. So that's sort of the gauge invariant way of expressing what you mean by the Hamiltonian. What you mean by the Hamiltonian is the set of numbers, the set of real numbers, which are the diagonal elements of the Hamiltonian matrix in the energy eigenbasis, i.e. the spectrum of the Hamiltonian, the set of energy eigenvalues, okay? So I'm putting it in this very stark, very bare bones way on purpose, because I want to drive home how intimidating this self-appointed task is. I'm saying that all we really are given, what we mean by the laws of physics in a bare bones quantum mechanical description is a set of real numbers, the spectrum of the Hamiltonian, the eigenvalues of the Hamiltonian. And from that, somehow, the world is supposed to emerge. So here is the known world in an equation form, right? This is the amplitude in the weak field limit in an effective field theory with what Frank Wilczek has dubbed the core theory, which is basically just the standard model of particle physics plus low energy limit, weak field limit of general relativity. It's all perfectly valid as an effective field theory, but there's an enormous amount of structure here. There's three-dimensional space, okay? It's not an arbitrary number of dimensions. I don't know about you, but I live in 3 dimensions macroscopically. There's gravity with a certain dynamics. There's certain gauge fields and not others, certain fermions and not others, certain scalars and not others. All of that should be implicit in the spectrum of the Hamiltonian. How in the world are we going to get from the spectrum of the Hamiltonian to that? And I won't get all the way there, but like I said, like I promised you at the start, I'm going to sort of show you the first steps in getting there. And there's plenty of work to be done. So you can write papers and then cite me. That would be great. I'm not going to prevent you from doing that. So how do we do this? What is the sort of mental space we have to be in when we're tackling this problem? How do we go from something that is as featureless as a list of energy eigenvalues to an interpretation in terms of physical structures? And this is where actually, thinking like a philosopher helps a little bit. Well, think about that Hamiltonian for the simple harmonic oscillator that we wrote in the position basis, where it's familiar and gives us a warm, fuzzy feeling when we see it. Why did we choose that? What was so great about that initially? Why do we start so often when we teach people quantum mechanics with classical physics in phase space and then writing down wave functions as functions of position in particular? Well, the answer is that the world is not a simple harmonic oscillator. There are simple harmonic oscillators in the world, but they are embedded in the world. They are part of the world. And we pick out a basis to describe things as our favorite because we interact with them. Basically, positions, not just harmonic oscillators, but the positions of the stars and the planets in the sky. What's so special about them? We see them when we look at them, okay? We can learn later on. There's always a little bit of a mental barrier when you learn about Hamiltonian mechanics, and momentum is treated on the same footing as position and so forth, because we see positions. We can measure momentum, we can infer it, but we don't see it exactly in the same way, right? So there's something special about the interaction between systems and the rest of the world that picks out position as special. Also something about the intrinsic dynamics, and we'll get to that. But basically, the hint that we're taking here is that the set of structures we're looking for don't arise just by looking at the Hamiltonian of the whole thing, but by dividing up Hilbert space into subsystems and then asking what is the best way to divide it up. And then given some way to divide it up or factorize it or decompose it, whatever you want to say, what do you infer about subsystems from observations from the rest of the world? And when is there a classical limit in particular? So this is, again, something we need to do on the basis of no information other than the Hamiltonian. The Hamiltonian is a map from Hilbert space to Hilbert space, right, to Hilbert space to itself. And if you give me a decomposition of Hilbert space, so if you factorize Hilbert space into a tensor product, there's a lot of things we could do. We could get more complicated with direct sums and things like that, but let's just do the simple thing that we learn when we talk about subsystems in quantum mechanics: factorize into Hilbert space A, tensor Hilbert space B. Once you do that, once you have such a factorization, the Hamiltonian comes along for the ride. You can decompose the Hamiltonian into the part that only works on system A, the part that only works on system B, and then the interaction, right? So what we're doing is we have something in mind that qualifies as a useful decomposition of the Hamiltonian. I'll have to specify what I mean by that in a second. But what we can do is imagine sifting through every possible tensor factorization of Hilbert space and asking ourselves for each, which is the most useful? We can optimize our decomposition of Hilbert space for some kind of usefulness. I'm beginning to speak in AI language now because we're in a new artificial intelligence world, so we got to adapt to the new regime here. So here's one criterion that we might use when we're looking for the right way to factorize Hilbert space. We can factorize Hilbert space into a system and an environment such that the system behaves classically, okay? Now, you might take a God's eye view and say, well, why? Why does a system behave classically? That's not what I'm doing. I'm actually taking hints from the real world. I know that in the real world, the classical approximation is pretty darn good. I can get a rocket to the moon, etc. So I'm just taking that for granted. I'm not being so philosophical, but I'm trying to explain the origin of classical behavior. That's for a later paper that I have coming out. But right now, just if there is classical behavior, can we find it? And when you took your quantum mechanics course when you were a youth, you were taught something about the classical limit, and probably Ehrenfest's theorem came in, right? If you have a small wave packet, small, it means small compared to the scale on which the potential is changing or something like that. The center of that wave packet obeys the classical equations of motion. And that's true, but it's not the only aspect of classical behavior. For one thing, why were you so fortunate to start with a classical looking localized wave packet in the first place, okay? There's secretly another thing going on that is really crucial to classical behavior. Think about Schrödinger's cat. Think about Schrödinger goes through this long rigmarole to get a cat in a state where it's in a superposition of awake and asleep. I don't like to kill the cat in my versions of Schrödinger's cat experiment. I just give it sleeping gas in the box, okay? But the point of Schrödinger's experiment is there is a superposition of two different macroscopic looking versions of the cat. I'm going to call one awake and one asleep. And his whole point is, surely you don't believe that's real, okay? But, you know, I'm taking a pure version of quantum mechanics in which that is real. But his better point is we never see it, right? We never look at the cat and see a superposition of two different, very classical, but very different macroscopic configurations. And why not? Well, we know, I'm not here to tell you the whole story, but we know the basic answer to that, at least in my favorite Everettian version of quantum mechanics. It's all about decoherence and branching, right? So if you start with a cat in a superposition of two different macroscopic states, it will instantly become entangled with the environment. In the figure here, maybe you can see my pointer moving around. In the figure here, you have an awake cat and a sleep cat. The photon will hit and be absorbed by the wake cat, but be completely non-interacting with the asleep cat. So that means that there's a differential interaction with the cat in the environment, depending on which of those two states it's in, which means there's instantly entanglement, okay? And that's what decoherence is. The environment's becoming entangled with the system right away. And in the Everettian language, you would then say it branches, and now you have two branches, one of which the cat's awake, one of which the cat's asleep. And the point that they don't tell you, but is really crucial here, is that once that branching happens, you don't keep entangling. If you have a cat that is in one macroscopic state, like it's awake, it will interact with the environment, but it won't entangle with it anymore because the photons either just absorb or bounce off, but they do the same thing. All of the photons do the same thing to the cat once it's on one branch of the wave function. So there is an aspect of classicality which says that you don't rapidly become more and more entangled with the environment. If you're in a superposition, then you do become rapidly entangled. That's because you're not classical to start with. But once you're localized in what we think of as a classical macroscopic state, the rate of increasing entanglement slows down. That's an important part of what it means to be classical. So there are basically two criteria for classicality. Localized states remain localized, unentangled states remain unentangled. That's what we will use, and this is a paper I wrote with Ashmeet Singh. This is what we call quantum mereology. The mereology is the study of the relationship between wholes and parts. We start from the whole, ask how to divide it up into parts. So given some purported candidate factorization of the Hilbert space into system and environment, we can write the Hamiltonian as a system part, environment part. We never care about the environment part. Who cares about what the environment's doing? And then an interaction part. Generically, if you start with some randomly chosen set of energy eigenvalues for a Hamiltonian, no possible factorization you can pick will lead to classical behavior of the system. But our point is that when you are lucky enough to have a Hamiltonian that allows for some classical behavior for a subsystem, we can find the right factorization in which that happens by implementing these two criteria, by looking at the Hamiltonian in this way. So quick reminder, there are things called pointer states. This is Zurek's, I think it's Zurek's term, but he uses it a lot anyway. I'm not sure if he coined the term, but these are the states into which the density matrix of a system will quickly diagonalize dynamically via decoherence. So simply put, there's an awake cat, that's a pointer state. There's an asleep cat, that's a pointer state, okay? So if you look at decoherence as there's a system subset of Hilbert space and an environment subset, and you look at the reduced density matrix for the system, you can always diagonalize the density matrix. That's trivial. But there's a non-trivial statement that dynamically, given the Hamiltonian, there is a basis ahead of time in which the system will become diagonal. That's a very non-trivial state. That's the pointer basis, okay? So the pointer states, like a live cat or awake cat, asleep cat, these are determined by the dynamics. They're ones in which you don't keep having extra entanglement. They are robust under being monitored by the environment. They don't themselves decohere. They're there, they look kind of classical. This is old stuff. What I want to introduce into your brain, if you're not already familiar with it, is the concept of a pointer observable. Pointer observable is just the observable who has eigenstates that are the pointer basis, okay? So the pointer observable is in some sense what the environment is monitoring of the system. Again, if you think of the awake cat and the asleep cat, the environment quickly decoheres them from each other, okay? Usually when you're looking at a pendulum rocking back and forth, what do you see with your eyeballs? You see the position of the pendulum. So Zurek is very careful, and he knows that there's some limits depending on what the dynamics does, but he defines the quantum measurement limit in which the interaction Hamiltonian rather than the system Hamiltonian is dominating what happens to the quantum state, and you can make that quantitative, and I'm not going to bother. But it helps you pick out what you mean by a pointer observable. Roughly speaking, these pointer observables commute with the interaction Hamiltonian. This is just the mathematical quantification of the idea that once you're in a pointer state, you don't keep getting entangled. You're not really affected by the environment anymore once you're in a pointer state. And so the pointer observable is the sort of way of saying that in operator language rather than state language. For example, just to get your intuition going, position is the pointer observable that we're most familiar with in the big macroscopic world. So this gives us, Ashmeet Singh and I claim, a way of mathematically characterizing what factorizations will lead to classical behavior. And for better or for worse, there are two things you have to simultaneously try to minimize. So there's a bit of an art form here that I think this is something that, quantum physicists could have discussed this very carefully in the 1950s, but they didn't. I think that it's time we get this right, the exact way to do this. So Ashmeet and I are proposing the following way of thinking about it. There's two things we want to minimize. We want a number that is dimensionless that characterizes each of them. One is the amount of localization of the system's reduced density matrix, and we quantify that using the entropy of the system's density matrix, okay? So if you have an initially, I'm just describing this backwards. We characterize the localization by what we call the pointer entropy So the pointer entropy, if you have the diagonal density matrix of the system, you just say, how spread out is it along the diagonal, okay? And it could be spread out or not, but the point is that the amount of spread we want not to grow with time. So that means that if you're in any one classical looking state, you just sort of evolve there without knowing about any of the other classical looking states. Your wave packet remains localized. That's the localization criterion, the pointer entropy. This actual entropy of the system itself helps you quantify the amount of entanglement with the rest of the world. That we all know, right? That's what we mean by the von Neumann entropy. If the whole state is pure, the von Neumann entropy of the subsystem is telling you how entangled it is with the rest of the world. Now, really, it should be minus trace rho log rho, but that's harder to calculate on our computer. So we use the linear system entropy as a way that we can actually do some numerical experiments here. But I don't think that should actually matter for the outcome in terms of what states are the classical ones. So we have two things that help us characterize the entanglement of the system and the environment and the localization of the system itself. And happily, those kind of map onto features of the system Hamiltonian by itself and the interaction Hamiltonian by itself. So this all kind of fits together with our intuition and with the math. And then we propose the algorithm. This is an algorithm for sifting through all possible decompositions of Hilbert space into what we hope to call a system and what we hope to call an environment and see which ones actually work. So for each factorization, you find the candidate pointer observable that does its best to commute with the interaction Hamiltonian, okay? Then you start in an unentangled state in an eigenstate of that pointer observable. So think of the cat is awake. That's an eigenstate of the pointer observable, or the Earth is at a certain position in its orbit. And then you look for all the factorizations you could possibly imagine. So this is a lot of factorizations. There's an infinite number. It's a numerically complicated problem. You minimize the growth rate of these two entropies, or the maximum of these two entropies, which we called the Schwinger entropy, the maximum of the linear entropy and the pointer entropy. I will confess that we have forgotten why we called it the Schwinger entropy. At some point, we were reading papers by Schwinger and they helped guide us somehow, but I forgot exactly why we got this idea for calling it that. So if anyone remembers or finds this, let us know. And then the idea is that the Schwinger entropy growth rate is minimized at what we would think of as the right factorization of Hilbert space into system and environment. So we did a couple of very simple numerical investigations here. Here's an example where you have two harmonic oscillators with a very weak interaction between them. And so that assumes a way of factorizing Hilbert space, right? When I just say the words, two harmonic oscillators, two heavy objects on springs with a weak interaction between them, that's already presuming you know what the right factorization is. So what this plot is we start with the right factorization, we calculate the Schwinger entropy, and then we randomly apply a unitary operator to Hilbert space to get away from the right factorization, to change the decomposition, and we recalculate the Schwinger entropy. And what we find is that indeed, for all of the wrong factorizations, that Schwinger entropy growth rate is larger than for the right one. This gives us some feeling that we're on the right track, that indeed minimizing this particular quantity is the right thing to do to define a decomposition of Hilbert space. So the claim at the end of the day is we don't need any extra information other than the set of eigenvalues of the Hamiltonian in order to figure out how to decompose Hilbert space into a system that can become classical, tensored into an environment. Let's go beyond that. Let's just take this as good news and move onward. We have more in the real world than simply a classical subsystem and the rest of the world. We have space and locality. Someone raised their hand. Do we want to
yes, just a small question, but what are the dimensions of these spaces that you were working with on the previous slide? Like, how big is the total dimension? Are they...
It's very, very big.
I see.
But I mean, in the actual numerical simulation that this plot was generated from, it's not that big because it's done on a laptop. But the Hilbert spaces we started with are infinite dimensional because they're harmonic oscillators, right? So we truncate it for the numerical experiment.
I see. And then you use that truncation to like sift through like, oh, if this space has dimension 2, this one has 98. I don't know. Let's say if it was 100 or something like this. And
yeah, it's much bigger than 2. It's more like, 2 to the 10.
Yeah.
Right.
Okay. Okay. Thank you.
Sure. Okay. So let's find more about the universe than just the existence of a classical subsystem. Let's find the features we know and love, space, field theory. We're not going to get there, not going to get all the way there, but it's kind of remarkable how far we get, even in our meager amount of work that we've done. So there is something called space. Most versions of quantum mechanics presume that there is something called space when you start, right? You have hidden variables in Bohmian mechanics that have locations in space, or you objectively collapse and by localizing in space, etc. In this hardcore, what we call mad dog version of quantum mechanics, space is nowhere to be found in the original specification of the theory. All you have is a list of energy eigenvalues, right? So how in the world is space supposed to emerge from that? And the answer is, what we can do is ask, what features does space have in the known version of physics? And then can we find those features just from the spectrum of the Hamiltonian? So let's think about known physics. Let's think about physics as we understand it. Quantum field theory, for example. We know that there is space, that there are quantum fields in space. Even though I'm saying quantum field theory, forget about particles and forces. Just think about the vacuum state, okay? Just think about empty space, the minimum energy state of a quantum field theory. And there's subtleties here with gauge theories and factorization. I don't care about any of those. Think about a simple scalar field theory if you want to. If I divide space, like real physical three-dimensional space, into subregions, then I can have as a basis for my quantum field theory independently vibrating fields in each one of those subregions, and that corresponds to a factorization of Hilbert space. So I can divide up Hilbert space into factors that represent regions of actual space, okay? This is standard stuff. I'm not trying to do anything crazy. And then, as we said before, once you give me a factorization, that gives me a form of the Hamiltonian. I go from just a set of energy eigenvalues to operators on those subspaces. So there's operators on each individual region of space, plus 2-point operators representing interactions, 3-point operators, etc. And I noticed that this is an infinite series. Any two of those or any n of those regions of space could in principle interact with each other, okay? But I know that in quantum field theory, they don't actually interact with each other. What actually happens is a region of space interacts with its nearest neighbors in some discretization of a quantum field theory. It does not interact arbitrarily with things far away. This feature is called locality, okay? And this is once again, a highly non-generic feature that a Hamiltonian could have, the existence of a factorization in which subfactors only interact with nearest neighbors. So a very weak version of this criterion is that each subfactor only interacts with a finite number or a small number, 5, I don't know, whatever number you want to pick, of its other subfactors, and we will ex post facto call those nearest neighbors. That will be a k-local Hamiltonian. And there was a very nice paper written a few years ago by folks who were at the time graduate students and now grown up to become much more accomplished, where they start with, it's called locality from the spectrum of the Hamiltonian. And they start with a finite-dimensional Hilbert space, just the spectrum, ask if you can derive what you mean by a local decomposition of Hilbert space. And they find the answer is yes. They find first that, again, a generic Hamiltonian has no local factorizations. There are fewer local Hamiltonians than there are Hamiltonians, in a very simple way of parameterizing things, okay? But happily, when there is a local factorization, it is essentially unique. There's some trivial reshufflings, et cetera, that you can apply. But basically, if you start with a spectrum of a Hamiltonian that has a local factorization, you can find it. Again, numerically, it'll be very, very hard to do, but in principle, you could sift through all the different possible factorizations of that Hilbert space, and you could know, this factorization makes the Hamiltonian look local, okay? So there is a preferred, in some sense, if you care about locality, there's a preferred way of factorizing a very, very big Hamiltonian into acting on little subspaces of it, which gives us this graph-like feature, right? So this graph that I've drawn here is representing not regions of space, but subfactors of Hilbert space. And the lines between them are, there is a direct interaction in the Hamiltonian between these two subregions, okay? But then when we interpret it as space, this is the emergence of space just from Hilbert space. Okay, so this is literally the title of our first paper with Charles Tsao and Spiros Mikolakis, space from Hilbert space. This is how it can emerge, because you're looking for, you want locality. It's not obvious, it's not easy, but when it's there, you can find it in principle. And then, all right, that I give credit to this other paper. So we're going to be a little bit more ambitious now. We want not just space, we want curved space. We want gravity. We want general relativity, okay? Now, there's an enormous amount of work being done in the general field of what is labeled gravity or space-time emerging from entanglement, okay? But in case you're not an expert in this already, it is almost all in the context of the ADS-CFT correspondence. So they imagine there's a boundary theory and a bulk theory, and it's the entanglement in the boundary theory that is being used to emerge geometry and curvature in the bulk theory. So it's in a different theory, okay? Which is great. I'm all in favor of that. I don't want to do it myself. There's plenty of other people doing that. And also, we don't live in anti-de Sitter space. I would like to understand why apples fall from trees, why the earth goes around the sun, things like that. So rather than looking at horizons and cosmology and black holes, let's just look at weak gravitational fields, slightly curved geometries. In that limit, in that set of circumstances, gravity looks like a local field theory, right? I gave you the partition function for it in an equation before, okay? It's a very local looking quantum field theory. How can we interpret that in terms of our finite dimensional Hilbert space and its Hamiltonian, okay? Well, again, here is this decomposition of space into regions, which I claim I can find just on the basis of the Hamiltonian. Now, let me look at the ground state of that Hamiltonian, okay? There's something we know from our experience of quantum field theory, which is that every two regions, every two subfactors of Hilbert space will be entangled with each other, but that amount of entanglement has a structure, and it's kind of the obvious structure you would guess. Nearby regions are highly entangled. Far away regions only have a tiny amount of entanglement. It never goes to zero. That's the basis of the Riesch-Leiter theorem. But it's there and it falls off. And the rate at which it falls off depends on whether you have a massless field or a massive field, et cetera, but it always falls off. So our proposal is, what I just told you was what we know about ordinary quantum field theory. Nearby regions are highly entangled, faraway regions less entangled. We are starting with a situation in which we don't have a metric to start. There's no distance measure, but there is an entanglement measure. We could measure the entanglement in the ground state. So let's turn it around. Rather than saying, when you're nearby, you're highly entangled, we're going to say, when you're highly entangled, you're nearby, and vice versa, okay? So that takes this graph that we made and puts a metric on it, okay? Again, generically, it wouldn't be a metric that in any sense describes a smooth manifold or anything like that. But in the cases when it does, you can figure out how to do it. You can figure out sort of a smooth classical geometry that approximates the metric that you've put on this discrete network. And I'm going to get a little technical here. It's near the end of the talk, so I'm allowed to be a little bit more technical, so we can, show off so that we did real work here. The way that we're characterizing the amount of entanglement between two subregions is the mutual information. So the mutual information tells you of the entropy of any one part, how much of that is because it is entangled with somewhere else. If you have high mutual information, there's a lot of entanglement. Low mutual information, there's very little. And what we're going to conjecture is that if I draw a boundary between one region of Hilbert space subfactors and another, the amount of mutual information between that region and its exterior defines what we would call the area of that boundary. So I gave you the simple-minded version on the last slide. The metric, the distance, is the amount of entanglement. This is a bit more sophisticated. The area is, and a bit more accurate. The area is the mutual information between a region and its complement, okay? And then there's a lot of fun math you can do with what is called the radon transform. The radon transform is used if you have a bunch of slices of something, you can reconstruct the whole three-dimensional thing. This is literally used in making images of your brain. We're going to use it to make images of space-time. We have a bunch of areas of surfaces, and we're going to say that defines the whole metric. Okay, I'm going to skip some details there, but I promise you that they're there. But I want to give you the spirit of what actually happens. So start with the ground state. Okay, so start with and now Unlike before, we were just looking at the Hamiltonian. Now we're looking at states, because the Hamiltonian can define locality, but obviously curvature is going to change from moment to moment. It's a dynamical thing. So we have to look at states, not just the Hamiltonian itself. So start with the ground state, which we assume looks like flat space-time, and we're going to perturb it a little bit. Okay, so if we perturb it in such a way that one factor of Hilbert space here is less entangled with the rest of the world, then by the philosophy that we gave you earlier, that means it's further away. The metric has changed a little bit, and we would interpret that in the continuum limit as there is spatial curvature at that point. And the hypothesis is, and this is just a conjecture, and we sort of need to check to see if it makes sense, et cetera. It's not a derivation. We conjecture that we can define an emergent area whose perturbation is proportional to the change in the mutual information under that perturbation, which is, as we can show, is just the proportional to the change of the entropy of that little subregion, if we pick out one little subregion at a time. So change in entropy change in area is proportional to change in entropy. That is the starting point of all of this effort. And then it's just math. And happily for us, the math has already been done by somebody else. Ted Jacobson has done this. Jacobson was trying to, in his famous paper about Einstein's equation as an equation of state, what he was doing was assuming that there was a space-time and a metric and looking at quantum fields on that space-time and perturbing them and looking at their change in entropy and area and so forth. We're doing basically the same thing, but we're emerging space-time itself as well. We're not putting space-time in from the start. So what Jacobson was able to do was show that in this continuum limit, that change in area is proportional to the scalar curvature, spatial curvature. We're in a certain gauge, if you want, synchronous gauge, where we're talking about spatial curvature, not space-time curvature. Change in area is proportional to the scalar curvature at that point, which is proportional to the 0, component of Einstein's equation if you embed that spatial surface in a space-time in the synchronous gauge, okay? So I know I'm going fast, and I'm just encourage you to read the papers here, but at the end of the day, the change of entropy of our little region of space can be interpreted as a change in the 0, component of the Einstein tensor of general relativity, the left-hand side of Einstein's equation. What about the right-hand side? Well, we want the change in the Einstein tensor to be proportional to the change in the energy momentum tensor. I haven't talked about energy or momentum or anything like that. Where does that come from? Well, there's a trick. There's a trick using what is known as the modular Hamiltonian. So you've heard that in quantum mechanics, if I have a density matrix for a system governed by a certain Hamiltonian, the thermal density matrix is the one that looks like e to the minus beta h, where beta is the inverse temperature and h is the Hamiltonian, okay? So if the state were thermal, it would look like e to the minus h. But we can do that backwards also. For any density matrix, we can always take its logarithm. So we can always write any density matrix as e to the minus k, where k is some operator. And you can interpret k as what the Hamiltonian would have to be in order for that state to look thermal. And we call this the modular Hamiltonian. It is not the Hamiltonian. It is a Hamiltonian-like operator we can construct from any given density matrix. But then you can show that this modular Hamiltonian has some nice properties. There's a wonderful relation known as the entanglement first law, which says if I take a density matrix, which I get just by having a pure quantum state for the whole thing, and then taking the reduced density matrix, I perturb the whole quantum state. That gives me a perturbation of the reduced density matrix. So I can calculate both its change of entropy and the change of the expectation value of the modular Hamiltonian, and they're equal to each other. That is a non-trivial fact that you can derive called the entanglement first law, okay? The change of the entropy of a subfactor of Hilbert space is proportional to the change in the modular energy. Keep that fact in your brain. The other fact is that in an appropriate infrared limit, if at the end of the day you're going to get something that looks like quantum field theory at low energies, then you can relate the modular Hamiltonian to the good old-fashioned energy momentum tensor of that quantum field theory. And the relationship is that the perturbation in the expectation value of the modular Hamiltonian is just the perturbation in the 0, component of the energy momentum tensor, i.e. of what we would call the energy density if we were in that frame, okay? So this is the connection between purely quantum mechanical things and what you and I would interpret as energy and momentum. And it's the one we want. So here's the whole picture. And I know I'm summarizing a lot of things. You can disbelieve, you can be skeptical at any one of these arrows, let's put it that way. But this is what needs to work in order for this program to fly. At the top, we have a conjecture. The conjecture is that when we do a perturbation to our quantum state and calculate the change of the entropy of a subset, we can interpret that as the change in entropy, the change in area of the spatial region that emerges from that factor of Hilbert space. Okay, that is the conjecture. We're going to propose that and see where we go. But then it's just math. That change in area is related to the Einstein tensor. That change in entropy is related to the energy density. So G00 is proportional to T00. Nothing that we've done so far is Lorentz invariant. We have not imposed Lorentz invariance from the start, but the appropriate Hamiltonian will give rise to Lorentz invariant in the continuum infrared limit. And if that's true, and G00 is proportional to T00, the only way that's possible is if all of G mu nu is proportional to all of T mu nu. So G00 proportional to T00 is what we derive. We impose Lorentz invariance, and we can question whether or not that works or not. That's perfectly valid. And we find that the only way for this to be true is if Einstein's equation work. So in other words, what we're saying is, with a bunch of conjectural statements, but perfectly plausible conjectural statements, the sensible way to interpret the dynamics of the metric that emerges on this Hilbert space is as a metric that obeys Einstein's equation. By itself, that's not super. The fact that we get Einstein's equation is not the surprise. There aren't a lot of covariant equations you can get when you're describing the relationship between curvature and stress energy. What's interesting is not that we got that equation, but the way that we got it, the procedure that we went through, which didn't start with space-time and energy at all, but you can see the outlines of how it appears. So there's plenty, it should be clear, I hope. There's plenty of work to be done here. I'll just re-outline the program so you can decide which papers you want to write about it. We start with nothing but Hilbert space and a Hamiltonian. We carve up Hilbert space, we decompose it, we do mereology to it by demanding that systems act classically when they're being monitored by their environments. We use entanglement to figure out what we mean by locality and space, and then we use the Hamiltonian to define what we mean by locality, and then entanglement to define what we mean by the metric, the actual distance on that local discrete structure that we derived. And we showed that in the weak field limit, it kind of naturally wants to obey Einstein's equation. We can imagine an alternative theory of physics, history of physics, where general relativity was invented much later than quantum mechanics and was discovered by thinking hard about the emergence of space in quantum mechanics. I think that would be a difficult history to live through, but we can imagine that it's there. So there's many issues that are remaining. I'm not claiming that we're right, but I do claim the following thing, that if you take quantum mechanics seriously from the start, and you don't bake in classical notions that you are familiar with, and maybe you want to bake them in, it's not embarrassing to do it, but if you decide you don't want to bake in classical notions from the start, there's a clear set of things you have to do to get the classical world out. We haven't done all of them yet, but we've taken the first few steps and they are promising. Thank you very much.
Fantastic. Thank you very much, Sean. Please join me.
15 minutes.
Sean. Yeah, precise on the dot. Yeah. That was great. So we have already a few hands. So we have, people will raise hands to the interface and ask questions. I think the first person to raise a hand was Western.
Yeah, it's
us. There's a room full of people there.
It's us.
Ciao, Francesca. We can't hear you too well, but try.
Let me see if this works.
Thank you.
Okay, that's much better.
Hi, Sean. Thank you so much for this talk. Of course, I've been following this research of yours, so this was a very nice summary of the state of the art. Let me tell you that I think, I want to tell you two things. I think that there was one part of the talk in which you were very cautious, but I think that you have something much more solid and much more deep than what you were presenting. So I think this is good. But there were also parts in which you were very, you look at very sure and of the ingredients that you were putting in. And I would like to propose that maybe this part is missing something. So let me start from the good news. The good news is the part that you presented in the end, in which you were proposing the conjecture of the proportionality between area and entropy. And so in your presentation, this looked at like a reasonable conjecture. I would like to say that it seems to me that there is something stronger there, because when you work in general relativity and you formulate general relativity in Hamiltonian manner with an Hamiltonian formulation, and you work in with a Hall's term in a fully Lorentz invariant context, starting from the Lorentz group, the Lorentz symmetry. In that case, the proportionality between area and energy, and therefore also area and entropy, takes a very natural form that is coded in what we call the simplicity constraint. So from the question of general relativity, you have this proportionality between a variation of the area that goes into a variation of the energy. Well, this corresponds, if you want, to a variation of the boost Hamiltonian, but this can be interpreted as a variation in energy. And so if you divide by the Euro temperature, this is indeed the variation in the entropy. So, I mean, what I'm trying to say is that the fact that if you start from the Hamiltonian structure of general relativity, you get this is not something that you need to conjecture. It's already written there in the equations, and it seems to me that it's not something emergent, it's something that is there from the beginning. So, okay, this was my first comment.
Actually, Francesca, is it okay? Can I respond to that comment and then we can go to your criticism first? Because I think this is a very, very important point that you're raising here. For folks in the audience who are not experts in general relativity, as Francesca is, let me just give you some background so you know the mental state to be in here. If you didn't have gravity, if you had a quantum field theory or a lattice theory or any other non-gravitational theory, and you had a region of space with degrees of freedom inside, and they were entangled with the exterior, it is very natural for the ground state of that theory to have the feature that the entropy is proportional to the area of the boundary. But non-ground states don't have that feature at all. In principle, I could get more and more entanglement so that the entropy of the region was proportional to its volume, not its area. So people were a little weirded out in like the 90s when they first started thinking about this, because since Boltzmann, entropy, the maximum entropy is proportional to volume, not area. In the ground state, it's proportional to area, though, so they thought, oh, that's weird. But the extra thing here is that gravity does change the picture, and the conjecture is that gravity changes the picture in such a way that if you try to increase the entanglement between inside and outside, you don't get the entropy going bigger than the area, you change the area. The curvature of space-time comes in to compensate so that it retains the idea that entropy is proportional to area. Now, Francesca, as you're saying, in general relativity, that's built in. That's not a surprise. That makes sense. But remember, I am not building in general relativity. I'm not starting with general relativity. I'm just starting with quantum mechanics. And so to me, it has to be a conjecture that remains true. And it might work, the conjecture, but I can't derive it from anything like general relativity. That would be cheating for me.
I see. Yeah, okay. But the reasonable conjecture, I argue, is reasonable.
It's a reasonable conjecture, yes. But anyway, tell me your criticism. That's what I'm interested in.
Yeah, okay. No, it's okay, but we can discuss this more. Let me also mention my other comment. That's
what I mean, yeah.
That is about the first part, or the way in which you were summarizing things in the end, saying we started with a Hilbert space and a Hamiltonian and no other ingredient. And this is the part in which I disagree. Because you know very well, there is this Kotler Pennington-Renard result of 2017, in which indeed you have a preferred factorization of the Hilbert space that is given by, as you very clearly presented, given by the states of the Hamiltonian and given by this requirement of locality. But in that work, they are assuming a Newtonian background time. So there is a hidden assumption there that so of course it seems like there is a natural emergence of a factorization, but it's not coming for free. It's coming from the fact that you have previously assumed another factorization between space and time. So if you first choose what is your time, what is your clock, then you can do all the things that you are saying. Now, of course, I like the idea that if we live in some classical world, maybe there is a sense in which, or for instance, in a cosmological setting, you may have a preferred clock. So then you can run all your arguments, all your construction, and this works well. So once you choose the time, you can reconstruct space. But if in quantum gravity we want to reconstruct space-time, then you cannot throw time into the game just from the back door.
Right. So I want to sort of half agree and half disagree here. What I am assuming something, but it's not Newtonian time, it's Schrödinger time. I am assuming the Schrödinger equation, and that has a T in it. It does not have an X in it. There's no space in there. So I think that I'm not starting from space-time. I'm starting from the Schrödinger equation defined on Hilbert space. And what we will emerge from that, hopefully, is space-time. But then there will be a relationship between that Schrödinger time and the time as measured by an observer in this emergent space-time, and that's work to show it. And of course, you would hope that something like Lorentz invariance and diffeomorphism invariance emerge also, perhaps only in some limit, perhaps only approximately, but you have to start with something. And I am absolutely starting by assuming the reality and fundamentality of the time parameter in the Schrödinger equation. You might want to start somewhere else, but if I don't have that, then I have nothing to work with because I don't have the Hamiltonian and I can't do anything.
Since you were mentioning different variants, and I see a lot of similarity between what you are doing and the networks that we use in quantum gravity with spin networks. So in that case, the different variants come from the fact that having a network is working already with a different variant object that doesn't rely on a choice of coordinates. So it seems to me that different variant is something you can get very easily as long as you work in that manner.
I will simply approve of that comment.
Right. Then we have Marius.
Hi, can you hear me?
Yes.
First of all, thank you, Sean, for the very nice talk. I'll be very brief because it's just a small and maybe silly clarification so that I get my head around the material. So if I take, I want to understand a bit what is how it works with telling apart the environment and the degrees of freedom you care about. So if I have two quantum oscillators coupled, okay, in that case, I could decide to call one of the two the environment.
Yeah.
And it's going to be completely symmetric. So does your scheme here tells you have two choices, or does it just tell you in this case you don't have an environment? Just to understand the...
Yeah, no, that's a perfectly valid point. In that particular toy example we did numerically, you could have called either one the environment. That's exactly right. It's hard to come up with a good toy example which is both numerically tractable on your laptop and doesn't cheat, kind of, by making it obvious what is the system and what is the environment. So we didn't want to cheat in that way. But I absolutely think that it would be very interesting to do an investigation of much more general systems where the system environment split looks a little bit different than in our numerical example. It's far from convincing, the evidence we have so far.
Okay, thank you.
Ding.
Hi, Sean. I have a question about the first 2 points on your slide. So basically, I want to ask to arrive at point 2, where you have a preferred factorization, do you need to introduce additional ingredients in addition to the Hilbert space and the Hamiltonian? In particular, do you need to assume particular states to derive the preferred factorization? Or does the factorization work for all states in the Hilbert space?
So this is a good point. So let me say 2 things, because it depends on what you're trying to do. If you're doing the Kotler, Pennington, and Renard thing and just saying, is there a local factorization of Hilbert space? The state has nothing to do with anything. That is purely a statement about the Hamiltonian and how you can factorize it. If you want to do what Ashmeet Singh and I were doing and divide things into system and environment, then there is a long story about what we're assuming about the arrow of time, right? Because you want to start in a state which is not maximum entropy, a state where branching can happen toward the future and not toward the past. So by construction, given any candidate factorization, the question we ask is, if you start in a state in that candidate factorization with 0 entanglement between the purported system and purported environment, how does it evolve over time? So in that case, we absolutely are looking for not, what is the ground state, but given a factorization, are there states that will look classical? And of course, there are plenty of states that don't look classical at all.
I see. So you do assume particular states for this construction.
Yes.
And in that case, I would like to maybe comment on my preferred understanding of what your result means. It seems, of course, you may not disagree, you may not agree, and just my personal view. It seems you're not deriving a preferred factorization by the Hamiltonian. What you derived is the preferred factorization by the state. It's what those states prefer for their factorization, so that classicality, for example, can be preserved. It's not a property of the Hamiltonian itself that gave rise to the factorization. It's actually the state that gave you the structure.
I don't think that's exactly right, because you have to carefully phrase the conditionalities in the statement we are making. The statement we are making is, given a Hamiltonian, is there a factorization such that there is a state that acts classically? We don't presume ahead of time anything about the state. We're asking whether it exists, and that only depends on the features of the Hamiltonian.
However, state does play a role. It's not that
the state plays a role, but only in the sense we're asking, given the Hamiltonian, does there exist a state that looks the way we want it to?
And you're not asking for example, this is a condition that can be met by just one state is enough.
Yeah, but again, and we're very, very practical people here. We care about the real world. In the real world, the universe starts in a very particular state and evolves over time, and that's what we want to ultimately describe. We're trying to get the real world right. Getting other worlds right is a higher aspiration that I'm too humble to shoot for.
Okay, thank you.
Right, then we have Carlo.
Hi, Sean, 2 questions. Very short, both of them, just to clarify. First of all, it's beautiful to see how this program of yours grows and becomes richer and more includes more things. So I'm following it with enormous interest. First question is it might be a triviality. Maybe you have an obvious answer, but it's more about intuition. Let me formulate this way. Suppose I'm a first-year physics student, and I study, I go to class, and they tell me about the quantum mechanics of 2 penduli, pendulums, penduli, I don't know, with a small a small coupling between the two, small interaction. And it's beautiful mathematics because I see the resonance, I see everything, and it's a rich phenomenology. I mean, you have this interesting trajectory in which one oscillates, and after a while, the energy slowly get transferred to the other, and all this stuff. But then I listened to a talk by Sean Carroll, and I say, Sean Carroll is great. I'm now a Sean Carrollian. So I take this system, okay, which I've been told at school, and say, I know that it's just the Hilbert space and a Hamiltonian. So I write the Hilbert space Hamiltonian, and then I think, okay, so let's see, what is the right factorization of that? I work out because I'm a good student, and I find that there are two modes, the eigenmodes, of course, where what is going on is just there are just two uncoupled modes. There's absolutely no interest in physics. It's just two things oscillating at different. I've missed something, obviously, because there is interest in physics. Now, if I go out and I ask Carlo, say, Professor Carlo, what's going on? I would say, come on, a system is defined by Hilbert space Hamiltonian and some preferred observables that are the ones that actually define the system. Now I say, no, Carlo doesn't understand Sean. So I go out and ask Sean, what is his answer?
Good. So it actually relates back to the question that just happened, I guess, from Ding was his name. Sure, you can always just like solve this. You can forget about. I mean, don't forget about. Let's rephrase the question. No matter what system I give you in a finite-dimensional Hilbert space overall, I can always choose to look at it in terms of the energy eigenstates. And there, the evolution is just trivial. All right, each energy eigenstate just circles around, in its little phase, and that you're allowed to do that. But there are other things you're also allowed to do. So the question that we're asking is there a way to factorize Hilbert space into such that it's not just the energy eigenstates, but a subfactor that is behaving in some classical way, obeying classical equations of motion and remaining relatively unentangled with its environment? And we found that the answer was yes in this particular case. Now, as I said before, this might not be the right case, the best numerical example to look at, but that's the question we're asking. We're not saying mathematically, what is the simplest way to analyze this system to exactly solve it? We're saying, is there a way to subdivide it so that a subsystem looks classical? It's a different question.
Okay, so short answer would be, no. The story about finding the proper tensor factorization of Hilbert space should not be applied to a simple quantum system by itself. It should be applied keeping the environment in mind. A simple quantum system itself, it sort of doesn't work well. It needs the full. Is that the answer?
Yep, that's the answer.
Okay. Second question, that's even shorter. It sort of has to do with your reply to Francesca a lot. You start ground, so you say, okay, I give you a full theory of the world, and then you answer Francesca saying, I need a Schrödinger time. Okay, so I assume that the world there is a Schrödinger time. Now, if I write classically the action of the standard model plus general relativity, which is the best description we have about reality so far, there is nothing that looks like the Schrödinger time there, zero. So what has happened? There is a fundamental Schrödinger time, and it's like confused by the classical limit. I mean, or formulate another way. I'm a student, and Professor Sean, is there a Schrödinger time in the universe?
Right. So I think it's actually easier to answer this question conceptually if we forget about gravity for the moment. And I know gravity is important, and it's really important for me, but let's just for the moment, for this question, forget about it. And imagining we're doing quantum electrodynamics, QED, right? And usually we would start with a space-time description and an action and do path integrals. Feynman taught us how to do this very, very nicely. But we could pick a Lorentz frame, write down the Hamiltonian of QED, and write down quantum states. And they would obey the Schrödinger equation with respect to that time parameter in that Lorentz frame. So That doesn't mean that that Lorentz frame is preferred in any way, because we know that we could have picked a different Lorentz frame and done the same operation. So in my program, we want that to work backwards. We're always doing everything backwards. What I'm saying is we start with a time, a Schrodinger-looking time, and a Hamiltonian, a set of states. And what should happen at the end of the day is that the dynamics have the property that ex post facto, when you solve for the evolution of the state over time, you realize there's a gigantic unitary transformation that you could do on all the states that would look like choosing a different Lorentz frame and using a different time parameter. So we absolutely need a Schrodinger time to start. That doesn't mean it is necessarily preferred.
So you think that in the final theory, after you and everybody else has worked out the full thing, there isn't a preferred Schrodinger time. There's a sort of huge covariance, which is much larger than we're bringing GR in, much larger than that Lorentz invariance, is in which all possible Schrodinger time can be chosen, but it's not of the kind of a Wheeler-DeWitt equation. It's not C psi equals 0. It's just what is a covariant version of this theory?
Yeah, I'm pretty non-dogmatic about this. I don't know. I'm just pointing out that choosing a certain time parameter to start and define the theory doesn't imply that that time parameter is preferred. So I see a possible future in which the best way of thinking about this theory is time is fundamental, space is not. But there's no preferred time parameter, and there's some unitary that trades between them. There's a whole nother future in which the time parameter that I'm using to currently define my theory is just a temporary way station, it's just a crutch. And what I eventually realize is there's another way of defining things where time itself is emergent. I literally can't do that straightforwardly in the program that we have right now, because if I start with the Wheeler-DeWitt equation, h psi equals 0, I have no information. I am in a single eigenstate of the Hamiltonian, and there's nothing to emerge anything from. Maybe the right, as we've discussed before, I think there's a possible conjectural way out, which is to say that this fundamental state of the universe is not a pure quantum state, but is a density operator. And then I have, the eigenvalues of the density operator to work with. But I need more to work with than just h psi equals 0 to get this program off the ground.
Okay. Yeah, clear. Thanks.
So there are more questions, but could I ask you to stop sharing the screen so maybe it's nicer we can see each other?
Of course.
So we had James Fullwood.
Okay. Hi, Sean. Thanks a lot for the talk. My first comment was basically Francesca's and Carlo's comment regarding this kind of time parameter, but I guess you've kind of answered that now. But I'm wondering, so perhaps there could be, if you think of time as perhaps being discrete, could you perhaps generalize this construction you have where the fundamental factorization of the Hilbert space starts with the factorization, a sort of temporal factorization, where you have factors corresponding to discrete time steps. And then in each of those temporal factors, then you have your factorization corresponding to space. Could something like that perhaps work? And I have one more comment after that, but that's my first question.
I have a template whenever anyone asks, could it possibly be true that X? I always say yes, it could possibly be true. I don't know. Again, I needed, as I said to Carlo, we need something to get off the ground. And we just picked that time was fundamental and went from there. There's plenty of work in making time be emergent from the quantum state itself. There are criticisms of that also, the clock ambiguity work by Albrecht, et cetera. And then there are responses to those criticisms by other people. And so that's a very interesting, worthwhile thing to think about. My bandwidth is finite, and I chose my poison. My poison is that I'd start the Schrodinger equation. I think there are pretty respectable places to start, even if it ends up not being completely fundamental.
Okay, thanks. And my second quick comment is about this emergent geometry that you have here based on mutual information. Mathematically, it makes a lot of sense to me, but kind of intuitively, something that's a bit not clear to me is that usually entanglement is sort of independent of distance, right? It's a sort of
not in the ground state.
Spatial correlation that's independent of distance, but here you're basing distance off of entanglement. So where's the kind of intuition behind that?
Because we're in the ground state. We're not talking about the entanglement between particles. If you think of particles, particles can have whatever entanglement you want, any place you want, right? There's no relationship, like you just said, between entanglement and distance. But if you think of quantum field theory, and you even think of a state with a lot of particles, think of the sun. The sun has a lot of particles in it. But if you draw a circle around the sun and count the quantum degrees of freedom inside that volume, they're almost all in their ground state, right? The number of excited states in the sun is still way smaller than the number of states. So to a very, very good approximation, as far as quantum field theory is concerned, the sun is the vacuum. And so when we're talking about entanglement, we're only talking about entanglement between the vacuum degrees of freedom.
Okay. Okay, thanks.
Then we had Deepak Vaid.
Hi, Sean. So first of all, I just want to thank you on behalf of all the students of general relativity for the beautiful notes and the beautiful textbook that bears your name. Then I have several questions. Let me ask them, and the moderator can stop me if I'm running over. The first question is that in the real world, we have matter. We have fermions and the Standard Model. But so you know, and Einstein's equation tells us that G mu nu is equal to T mu nu, where T mu nu comes from these matter fields. So where do you see matter coming from in your construction?
Yeah, it's there in the quantum state, just like it always is. You know, I always, again, in the slightly longer version of the talk, or in different versions of the talk, I tell the story of the Sine-Gordon theory and the massive Turing model. This is something that is pretty well known to condensed matter physicists under the name of bosonization. But Sidney Coleman and friends back in the 70s showed that you can start with a 1+1 dimensional bosonic field theory, the Sine-Gordon model, and a 1+1 dimensional purely fermionic theory, the massive Turing model. And you quantize them and you get the same theory. So the quantum theory of these two classical precursors is the same, even though one has nothing but bosons in it and the other one has nothing but fermions in it. And the lesson of that is that the quantum theory doesn't know or care whether it's quote unquote really bosons or fermions. The question from the quantum first point of view is, given the quantum theory, given the Hamiltonian and its evolution, what is the best classical way to take a limit and think about it? And so that will be, we haven't done it yet. I mean, I'm not trying to be arrogant. I'm trying to be as humble as we can. We don't know the best way to start with purely a Hamiltonian and say, these are the quantum fields that a person living in this universe would recognize. That's a very, very good open question, but ultimately it has to come from the eigenvalues of the Hamiltonian.
Okay. My second question is that, I mean, the dominant paradigm for quantum gravity is string theory. And in string theory, you traditionally derive or obtain Einstein's equations by, you know, looking at these renormalization equations. And you obtain you know, classical geometry in some sort of limit, low energy limit. But in these constructions of yours, it seems there is no need for any of that. There's no need for supersymmetry, for instance. There's no need for, you know, well, string theory. So, I mean, now I would like to think that, you know, string theory does have a role to play in quantum gravity. And so how do you think that string theory and these constructions could be reconciled?
Well, I'll say two things. One is that in principle, I think you could do, I think that the approach that I'm taking is not necessarily the best approach, but I do believe that it has some essence of correctness about it. In other words, I do think that it makes sense to start with the Schrodinger equation and a Hamiltonian and see what you can get from it. It might very well work out that what you get is essentially string theory in some sense, right? In some limit or some part of string theory or something like that. I mean, just looking at the ADS-CFT correspondence, on the one hand, we have just a conformal field theory without gravity. On the other hand, we purportedly have string theory in a 5-dimensional ADS crossed a 5-dimensional sphere, et cetera. The map there is always a little bit tricky when you're looking at sub-curvature length scales on the ADS side of things. So it might very well work out that there is a regime in which the real world looks string theory-esque, but also a regime in which the string theory description is not what the real world is doing. And so I don't know. I mean, I think that's an open question. I'm not prejudiced as to whether or not there is a string theory limit or not. The other thing is, I have asked string theorists, I've said, can I draw a circle around a region of space-time and look at the Hilbert space and ask whether it's finite dimensional or infinite dimensional? And they've told me that it's finite dimensional. So I think that it is completely compatible with everything that I've done here, even though the connection is not completely there, explicit.
Thanks. I agree with your perspective that, it might be more profitable to view string theory as a sort of an effective theory, which is valid over some range of scales rather than every scale.
Yeah. And by the way, let me just say one more thing, because I remember you mentioned supersymmetry, et cetera. The hidden benefit of this approach that I'm taking is that because Hilbert space is locally finite dimensional, there are no infinities. There's no quantity that can be infinite. All of the infinities of quantum field theory or whatever are remnants of the fact that you are extrapolating the reality of quantum field theory well beyond its appropriateness, to scales that were much smaller than were valid. And so everything I'm doing is completely compatible with effective field theory, but it just erases all infinities from the theory to start. So supersymmetry may or may not be a part of it, but maybe, arguably, possibly, the need for supersymmetry is less than you might think.
All right. I have one last, I'll just make it very quick. It's about the emergence of classicality, since you mentioned that in the beginning of your talk. And there's some very beautiful recent work by Scott Aronson, and I think in collaboration with Leonard Susskind and one more person, where they argue that essentially it is the complexity of a quantum state which tells us whether or not it's classical, or how close to being classical it is. So I mean, that's just something I thought was worth pointing out, because in that sort of picture, you don't really need to worry about many worlds and branches and all that. You just have a notion of complexity, and complexity determines classicality.
So it was a short question. I will give a short answer, which is that I think that they should worry about questions of decoherence and things like that, even though they don't.
Okay. Thanks a lot. Thanks a lot, Sean.
Sean, by the way, if you need to go away, you can.
I'm okay for a little bit longer. There's good questions here.
Yes. So there was a question by Simone Speziale, what to leave, but I'm going to read it. He left it in the chat. I think it's quite clear what the question was. So he was asking whether the analysis required an assumption of non-degeneracy of the energy spectrum, and if it would work even if the energy spectrum was degenerate, in particular, if the minimum eigenvalue is such that there are infinitely many ground states. But I guess, okay, right. That was this question.
The short answer is I don't know. Certainly for convenience purposes, we have always assumed the energy eigenspectrum was non-degenerate. I really want the Hilbert space to be finite dimensional. So if by infinitely many you mean there's a two-dimensional subspace and I can rotate on a continuum, I don't think that would change the analysis at all. If by infinitely many you mean there's an infinite dimensional subspace of vacuum states, that would be problematic. I don't think that would fit into with what I'm saying.
Sorry, just a short comment. Isn't this discussed in Kotler, Pennington, Reinhardt? They were allowing the degeneracy, I think, but they were saying that it has the degeneracy introduce a zero measure into the.
I think that's right. When I'm saying I'm always assuming non-degeneracy, I mean literally me. I don't mean it needs to be assumed. I'm just making my life easy exactly because I don't think it matters.
Okay. So since I'm already talking, I wanted to ask you about the result locality found in the spectrum. I was looking at it today, and there is this rebuttal that appeared recently that is the most cited paper that cites this paper that says that whenever the construction works, it is highly degenerate somehow. I don't know if you've heard of this. I can give you a more precise reference.
I've not heard of this. No, you got to send it to me. Yeah.
Oh, okay. Okay. Well, then.
So I can't really
read it. So yeah, exactly.
I'm glad people are talking about it. Good.
Right. And then I have another question about the last part of your talk, where you introduced the modular Hamiltonian, and I was a bit confused for a second because I didn't exactly understand how that fit, because you had this Hilbert space, and then you use the decomposition to find these subspaces that are k-local and so on, and then you identify a region, and then you associate to the region an energy, like a modular Hamiltonian.
Well, you associate to it a reduced density matrix.
Right, because you have the state.
Then you can always define a modular Hamiltonian in terms of that reduced density matrix. And then, as usual, we appeal to what we know about the real world in quantum field theory, which is that if you're in a regime where it looks like you're in the infrared regime of some field theory that has some massless particles, we know that the modular Hamiltonian is related to the actual good old energy density in a certain way. And
so you say whatever modular Hamiltonian I got just from the density matrix, I call that the energy. Or something exactly. Related to that.
The perturbations are proportional. Yes, that's right. And by the way, again, because it's a talk and there's only a finite amount of time, I say things as if they are true. In the paper that I wrote with Charles Tsao, the way that we phrased this entire program was, here is a set of assumptions under which we get the conclusions we want. And we boiled our assumptions down to like 11 different assumptions. And any one of them might be wrong or might be right. I'm sure that some of them can be derived from simpler assumptions, et cetera, but it's very much an if-then kind of statement right now.
Okay, great, thanks. There's a couple more people that had the hand raised. So there's Yuting Bai.
Okay, good night, can you hear me?
Yeah.
Okay, so I have two brief questions on the presentation you've just given. That is, the first question is about symmetry. That is, if according to your presentation, if I have a spectrum of the Hamiltonian, then I could indeed have an emergent spacetime. And my question is that for all possible spectrums of a Hamiltonian, would the emergent spacetimes have all the same symmetries in our real life? That is, the translational symmetry and Lorentz symmetry, etc. Or if it is not the case, what would be the constraint on the eigenvalues or the degeneracies of the Hamiltonian? Since all this information, if this is possible, then all the information of the symmetry should be included from the beginning in the spectrum of the Hamiltonian itself. Could we identify it directly from the beginning?
I think the answer is yes, you should be able to identify it, but it might only be an approximate symmetry, right? It might not be an exact symmetry. In fact, typically it won't be. I mean, there's a well-known theorem that I'm going to get it. I always forget all of the assumptions that goes into it, but there are no faithful representations of non-compact symmetry groups on finite dimensional vector spaces, okay? So if you want something like good old-fashioned Lorentz invariance or translation invariance, which are non-compact symmetry groups, and your Hilbert space is finite dimensional, you're not going to get an exact match there. but we know that they can be approximate. You know, in the Kotler et al. Construction, they have a finite-dimensional Hilbert space in which they are able to show that, you know, you can get locality in a sort of a lattice, very straightforward kind of thing. We know a lattice is something that isn't rotationally invariant or translationally invariant, but is approximately so. So I think that's what you would have to aspire to in this kind of construction, that you might get symmetries that are emergent not only in the classical limit, but also in the infrared limit.
Oh, and okay, and for the other question, that is, how can you ensure that the spacetimes you emerge from the original spectrums are all the same? So do you?
Oh, sorry. Do you? Well, maybe I misunderstood the question, but what Kotler et al. Claim is that given the spectrum, there's more or less a unique local representation of it. You know, I want to emphasize over and over again that this is not going to work at all for generic Hamiltonians. The Hamiltonian of the world is not generic. That's an interesting question all by itself. Why is the Hamiltonian of the world admitting a local description, a classical description, etc.? In fact, I would be perfectly willing to accept if someone didn't like my whole program and said, look, the existence of space and Lorentz invariance and things like that is evidence that space and Lorentz invariance are fundamental. I get that. I would, you know, I would acknowledge the strength of that argument. And I'm just sort of, in my point of view, the Hamiltonian of the world, we're just lucky that it allows for this description.
Yeah, and okay, and for the second question, the second question is a little bit about spin. That is, if you recall how Dirac derived the so-called Dirac equation, he starts from the relativistic Hamiltonian, but he noticed that there's a square root, and he don't want to square this square root. So he invented the so-called Dirac algebra, and he got the Dirac equation naturally. But my idea is that since your method works, if you know the spectrum of the Hamiltonian, so is it possible that we could, for a relativistic particle, we define the Hamiltonian directly by its energy spectrum, and then from this energy spectrums, we might emerge not only the space-time structure but also the spin of the particle.
Yeah, absolutely. That has to happen if the whole program is supposed to work. You know, we haven't derived. Other people, by the way, have looked at sort of finite-dimensional Hilbert spaces and asked how things like fermions and spin and gauge fields, et cetera, can emerge from them. But that's not been my focus yet. But, you know, if you just take a bunch of qubits on a lattice, you can get an infrared limit that looks like a fermion. So I think that's not any fundamental worry.
Okay, thank you very much.
Then we have Arthur.
Thank you, Sean, for your talk. I just have maybe slightly more simpler question. Just how do you see the Minkowski metric coming from this? Just the signature, for example, how would you see it, and how would you arrive at, like, for instance, the speed of light? Is it coming from, for instance, some Lieb-Robinson bound or something like this? Or is this essentially part of this page of conjectures that you had, where you were saying, oh, I can relate G00 to T00, and I'm conjecturing that if I wanted a Lorentz invariant theory, I would have to be able to extend this in a covariant manner. So are you inputting Lorentz covariance by assuming this conjecture, or can you somehow see the speed of light and a Lorentzian signature, for example, coming from this description?
Yeah, I think the signature is not going to be hard, but I think the speed of light is going to be something that has this non-generic character, that there's something about the Hamiltonian. Maybe it is a Lieb-Robinson bound kind of thing. That would be a very, very natural place to look. I've, scribbled some things down about that, but haven't gotten very far. But that is not something that we claim to have derived in any way. I would love to see that come out more explicitly. Look, I'll put my cards on the table and maybe give away something, but the hope is that we're not exactly Lorentz invariant, right? That would be the best thing, if you could actually calculate an experimental prediction, quantify the deviation from perfect Lorentz invariance, because I think that it should be there. My first ever published paper was violating Lorentz invariance. I thought it was the end of my physics career, but since then it's become a very popular paper. So I think that this is a way to go. Lorentz invariance shouldn't be held sacred.
Great, thank you.
John, I love this last comment and going in the direction of measure something, but we have this very, very strong bounds, experimental bounds on Lorentz invariance. So can you just say one sentence more about how this hope of yours could be compatible with the constraints we have?
Sure. You can violate Lorentz invariance, but there's only one way to be Lorentz invariance and an infinite number of ways to not be Lorentz invariant. It's like Tolstoy and the Happy Families. There's a kind of natural, dumb, naive way to violate Lorentz invariance by taking a field theory and putting it on a lattice and seeing that the dispersion relation of quantum fields is affected by the lattice spacing and goes to Lorentz invariant form as lattice spacing goes to 0, and then putting some experimental limit on the propagation of photons from far away, blah, 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 blah. But that's not the only way to violate Lorentz invariance. And in particular, I don't think that space-time is a lattice. I think that there are non-local things going on. So I think there's a lot of subtleties, and there's been amazingly good work done in the phenomenology of violating Lorentz invariance and how to test it. There's been less work done, because we don't know where to start, on deriving from first principles what the Lorentz violations should be. So I think there's plenty of phase space out there for explicit predictions that have not yet been ruled out.
Thank you. Very interesting.
There was a question in the chat by Anton. I don't know if he's still here. He could unmute themselves.
Let's call this the last question, because it is getting late here. Yeah.
All right. That was great. Well, I think it's a good question to end on. So what does your program say about space-time singularities?
Yeah, great.
There it is.
It completely solves any riddles about space-time singularities, because again, everything is finite from the start. Anything that you get in starting with a field theory, either classical or quantum, and pushing it so far that you run into a singularity or an infinity, from my perspective, is clearly an artifact of pushing your continuum theory beyond where it is applicable. It's supposed to be a limit in some sense. Now, that doesn't tell me what happens inside a black hole, okay? So I know there's no singularity there in my theory, because everything is finite. I don't know what there is. I don't know, how information gets out or anything like that. So I don't even know how to put in holography into this description. I have ideas. These are other things I've scribbled down, but we very explicitly were humble to start and are working in the weak field limit where there's no horizons, no cosmology, no singularities, and we want to get that out. We want to know why apples fall from trees. There's a very clear set of next steps. One is, among the next steps are, where do fermion and gauge fields come from? Another step is, where does Lorentz invariance come from and is it violated? Another one is, how does holography and horizons work in this theory? So full employment. I think there's plenty more to be done here.
Thank you.
That's a great note to end. So thank you again, Sean. That was a great talk and Q&A.
Thanks everyone for staying up.
Yes.
Thank you.
Bye-bye.
Goodbye.